The annealing furnace stood 4 stories tall in the center of the steelworks hall, a structure of red brick and iron banding that had operated without incident for 32 years. Its walls were 3 feet thick at the base, tapering to 18 inches at the crown. 12 wrought iron bands encircled the exterior at regular intervals, each band 4 inches wide and 3/4 of an inch thick, bolted tight with squared ends and heavy nuts. The furnace had been built in an era when permanence was assumed, when stone and iron were thought to obey their masters without complaint. Men who worked near it knew its moods. They knew the color of its brick face at full heat, the particular smell of hot masonry and scale, the way the air wavered above the charging doors when the interior glowed white. They knew how long it took to bring the furnace up to annealing temperature, how much coal the fireboxes consumed in a day, how the draft pulled when the dampers were set correctly. The structure was predictable. It was trusted. The furnace had been shut down 10 days earlier for inspection and minor repairs. Firebrick had been replaced in 2 of the lower chambers. Charging doors had been reseated. A cracked arch in the secondary flue had been torn out and rebuilt. The work was routine. When the masons and fitters completed their tasks, they found nothing alarming. The structure was sound. The ironwork was tight. Everything was as it should be. On the morning of reignition, the furnace stood cold and quiet. Its brick faces were dark grey, streaked with years of soot and scale. The iron bands showed surface rust, but no distortion. Workers passed it without concern. Superintendents reviewed the firing schedule and saw no reason for caution. Slow heat was the rule. The fire would be raised gently over 2 days, bringing the enormous mass of masonry up to working temperature without shock. This was standard practice. This was how furnaces were always brought back into service. No one suspected that the structure contained within itself the conditions for its own destruction. The fire was lit in the lower fireboxes just after dawn, small coal, carefully banked. The draft was kept low. Heat began to creep into the lower chambers, warming the firebrick lining before reaching the main walls. Temperatures were monitored by eye and by the color of the interior through observation ports. Everything proceeded as expected. By midday, the lower third of the furnace was warming. The brick faces remained cool to the touch on the exterior, but the interior was beginning to glow a dull red. Firemen added coal in measured amounts. The draft was opened slightly. Heat climbed at the prescribed rate. Supervisors checked the furnace twice during the afternoon and noted nothing irregular. On the second day, firing continued. The middle chambers were brought up to temperature. The upper sections began to warm. The entire structure was heating, slowly and steadily, exactly as it had been heated dozens of times before. Men worked nearby without concern. The charging cranes were prepared. Steel billets were staged for loading. The furnace would be ready for annealing by the following morning. Late in the afternoon of the second day, the interior temperature reached annealing range in the lower chambers. The firebrick lining glowed orange. The draft pulled strongly. Everything was normal. The firemen banked the coal for the night, maintaining heat without increasing it. The furnace would soak overnight, equalizing temperature throughout its mass. But the mass was not equalizing. The lower walls were hot. The upper walls were still cold. The interior faces were expanding. The exterior faces were not. The iron bands, bolted tight, held the masonry in rigid compression. Inside the brick, forces were building silently, locked into the structure by restraint and time. The furnace was loading itself with stress that had nowhere to go. The first crack sounded at 9:30 in the morning. It was not loud, but it was sharp and clear, cutting through the background noise of the works like a chisel striking stone. Men near the furnace stopped and turned. One of the firemen stepped back from the firebox door, looking up at the structure. For a moment, nothing else happened. Then a second crack echoed from higher up, followed by a third, softer but distinct. A thin vertical line appeared in the brick face on the south side, running from the base of the second iron band upward for perhaps 3 feet. Dust sifted from the fracture, drifting downward in a pale stream. The line was hairline thin, barely visible, but it had not been there an hour before. The head fireman called for the superintendent. Men gathered at a distance, watching the furnace. Another crack sounded, this time from the north face. A second fracture appeared, jagged and wandering, splitting the mortar joints between bricks and then cutting through the brick faces themselves. More dust fell. Small fragments of brick detached and clattered to the floor. The superintendent arrived and stood staring upward. He ordered the firing reduced immediately. The draft was closed down. Coal addition stopped. The furnace was to be cooled as quickly as safety allowed. But even as the orders were given, more cracks appeared. The sounds came in irregular intervals, sometimes single sharp reports, sometimes clusters of smaller pops and snaps. The fractures spread across the brick faces like veins, branching and connecting. One of the iron bands began to sing, a low metallic hum that rose and fell as stress redistributed along its length. The sound was unsettling, as if the band itself were alive and straining. Men stepped farther back. Some left the area entirely. The furnace was tearing itself apart, and no one understood why. The firing was stopped completely. The fireboxes were damped and sealed. The draft was closed. Heat input ceased. By all logic, the furnace should have begun to stabilize. Instead, the cracking accelerated. Fractures multiplied across the south and east faces. Entire sections of brick bulged outward slightly, pressing against the iron bands. The bands groaned under load, their bolted connections creaking. Dust continued to fall in steady streams from widening cracks. The sound of settling masonry became constant, a grinding, shifting noise that filled the furnace hall. The superintendent ordered everyone back. A cordon was set at 50 feet. Engineers were summoned. Messages were sent to the design office. The furnace was still hot inside, glowing red through the observation ports, but it was destroying itself without any increase in temperature. If anything, the damage seemed to worsen as the structure cooled. By afternoon, vertical cracks had propagated from the lower bands nearly to the crown. Horizontal cracks appeared along mortar joints, following the bedding planes between brick courses. The masonry was fracturing in a pattern that suggested internal forces far greater than anything the structure had been designed to resist. The iron bands, meant to reinforce the walls, seemed to be contributing to the destruction rather than preventing it. One engineer knelt at the cordon and studied the cracks through field glasses. He noted that the fractures were widest near the bands and narrowest between them. He noted that the south face, which had been nearest the fireboxes, was more damaged than the north. He noted that the cracks had appeared first in the lower sections and propagated upward. He said nothing, but he was beginning to understand. As evening approached, the cracking slowed but did not stop. The furnace stood fractured and distorted, its brick faces split and bulging, its iron bands stretched and humming with tension. It had been brought back to life gently and carefully, and it had responded by breaking itself apart. Attention turned to temperature. Thermocouples were installed where they could be safely placed. Measurements were taken through observation ports at different heights and on different faces. The readings revealed what the eye could not see. The lower chambers were still above 600 degrees. The middle chambers were cooler, perhaps 400 degrees. The upper sections were barely warm. On the south face, where the fireboxes were located, the interior wall was significantly hotter than the north face. The east and west faces fell somewhere between. The furnace was not a uniform body at uniform temperature. It was a patchwork of hot and cold regions, each expanding or contracting at different rates. The implications were profound. Brick expands when heated. The expansion is small, measurable in thousandths of an inch per foot, but in a structure 40 feet tall and 20 feet across, those small changes accumulated into inches of total movement. The lower walls, heated first and most intensely, had expanded. The upper walls, still cold, had not. The result was differential movement, with the bottom pushing outward while the top remained fixed. But the walls could not move freely. They were bound by the iron bands, cinched tight and bolted, designed to hold the masonry in compression and prevent bulging under internal pressure. The bands did their job. They restrained the expansion. They forced the brick to absorb the stress internally rather than displacing outward. And brick, strong in compression but weak in tension, responded by cracking. The south face had cracked first because it was heated first. The fractures propagated upward as heat spread. When firing stopped and cooling began, the process reversed. The outer faces cooled faster than the inner faces. The exterior brick tried to contract, while the interior remained expanded. New stresses formed, pulling the masonry apart from within. The damage continued because the temperature distribution remained uneven. The furnace was a battleground of competing forces, all generated by nothing more than heat and restraint. Engineers examined the iron bands more closely. Each band was a continuous loop of wrought iron, drawn tight around the furnace and bolted at overlapping ends. The bands had been installed when the furnace was cold, fitted snugly against the brick, and tensioned to a predetermined tightness. They were meant to counteract the outward pressure of gases and materials inside the furnace during operation. They were not meant to restrain thermal expansion. Iron expands when heated, but not at the same rate as brick. Brick expands roughly 5 parts per million per degree Fahrenheit. Wrought iron expands nearly 7 parts per million per degree. In a cold furnace, the difference is irrelevant. In a hot furnace, the difference creates conflict. As the furnace warmed, both the brick and the iron expanded. But the iron, heating from the outside by conduction and radiation from the hot brick, expanded faster and more uniformly. The bands grew longer. They pressed harder against the brick. They increased the compressive load on the masonry. At the same time, the brick beneath the bands was trying to expand outward. The bands resisted. The brick cracked. The mismatch was compounded by the banding pattern itself. Each band encircled the furnace completely, creating a rigid hoop. Between the bands, the brick was free to expand slightly, bulging outward in the gaps. At the bands, expansion was blocked. The result was stress concentration, with maximum tension in the brick immediately adjacent to the ironwork. The fractures followed the bands because that was where the stress was greatest. Material mismatch was not the only problem. The bands themselves were under tension, stretched by their own expansion and by the outward pressure of the brick. As the furnace cooled unevenly, the bands contracted at different rates on different faces. The south-facing portions, still hot, remained expanded. The north-facing portions, cooler, contracted. The bands distorted, pulling unevenly, loading the masonry in torsion and bending as well as tension. Brick and iron, both ancient materials, both trusted, were at war with each other. The engineers traced the failure backward. They examined the fracture patterns. They calculated expansion coefficients. They estimated temperature gradients. Slowly, a picture emerged of what had happened inside the furnace walls. When the lower chambers were fired, the inner faces of the brick walls heated quickly. The outer faces remained cold. The temperature difference across the wall thickness created a thermal gradient. The inner brick expanded. The outer brick did not. The wall tried to bow outward, with the hot face growing longer than the cold face. But the wall was part of a continuous structure, locked into the courses above and below, bound by mortar and weight and the iron bands. It could not bow. The stress had nowhere to go except into the brick itself. Brick is ceramic, brittle and strong in compression, but fragile in tension. When tensile stress exceeds the material's capacity, it fractures. The cracks began on the inner faces, where tension was highest, and propagated outward through the wall thickness. They followed the weakest paths, through mortar joints and across brick faces, branching and multiplying as stress redistributed around each new fracture. The iron bands, meant to strengthen the structure, acted as stress risers. They concentrated load at discrete points rather than distributing it evenly. They created sharp transitions between restrained and unrestrained sections. They turned a gradual expansion into a series of sudden, localized failures. The damage was not caused by overheating. It was not caused by overloading. It was caused by the simple act of warming a massive, rigid structure unevenly while preventing it from moving freely. The furnace had contained enormous internal forces, locked into its masonry by temperature difference and restraint. Those forces had been invisible, unmeasurable by the methods available at the time, but they had been real and they had been destructive. The furnace had cracked itself apart because it could not expand. It had continued cracking as it cooled because the temperature distribution remained uneven. The structure had been its own enemy. The engineering explanation was documented in reports that circulated among furnace designers and steelworks superintendents. Thermal expansion, once considered a minor nuisance requiring small clearances and loose fittings, was revealed as a force capable of destroying massive structures. Differential heating, long understood to cause warping in thin metal plates, was shown to generate internal stresses in thick masonry walls that could exceed the material's tensile strength. The concept of restraint stress entered the vocabulary. A material free to expand will expand without damage. A material prevented from expanding will generate internal force proportional to the restraint. In the annealing furnace, the restraint came from multiple sources. The continuity of the masonry, the weight of the structure above, the iron bands cinched around the perimeter, and the temperature gradient across the wall thickness. Each source contributed stress. Together, they overwhelmed the brick. Material mismatch was recognized as a critical design consideration. Brick and iron, when bonded together in a structure subject to temperature change, would fight each other unless provisions were made for differential movement. The iron bands, installed with good intentions, had worsened the problem by imposing rigid restraint at discrete locations. A better design would allow controlled expansion, either through flexible connections or through deliberate gaps that could close and open as temperatures changed. The failure also revealed the dangers of uneven heating. Firing a large furnace from the bottom created a vertical temperature gradient that guaranteed differential expansion. Firing from one side created a horizontal gradient. Both produced stress. The only way to minimize damage was to heat the entire structure as uniformly as possible, or to accept that cracking would occur and design for it accordingly. The furnace had not failed because of poor workmanship or defective materials. It had failed because the physics of thermal expansion, restraint, and material mismatch had not been fully understood when the structure was designed. The failure was a lesson, harsh and expensive, but clear. Heat does not only soften and melt, it also loads structures invisibly, creating forces that can destroy from within. The annealing furnace was rebuilt over the following months. The damaged brick was torn out and replaced. The iron bands were removed entirely and replaced with a different system of restraint, one that allowed controlled radial expansion through sliding connections and deliberately loosened fittings. Expansion joints were cut into the masonry at regular intervals, vertical slots filled with insulating fiber that could compress as the walls expanded. The firing procedure was revised. Heat would be introduced more gradually, with multiple burners placed at different heights and on all sides to minimize temperature gradients. Temperature monitoring would be more thorough, with thermocouples installed permanently at key locations. If differential heating was detected, firing would be adjusted or halted until the structure equalized. The lessons learned at this furnace were shared throughout the industry. Other furnaces were inspected. Many showed similar cracking, though less severe. Some were modified. New furnaces were designed with expansion joints and flexible restraints from the beginning. The assumption that masonry structures could be treated as rigid and unchanging was abandoned. Thermal expansion became a standard consideration in furnace design, along with draft, insulation, and refractory selection. The workers who had witnessed the cracking never forgot the sound. The sharp reports echoing through the hall, the dust falling from fractures, the low hum of iron bands under tension. They had seen a trusted structure turn against itself, breaking apart not from violence or neglect, but from the simple act of warming up. It was a reminder that the materials of industry, no matter how solid they appeared, were governed by forces beyond the visible. Heat moved through steel and stone silently, expanding and contracting, loading and unloading, creating stresses that could remain hidden until the moment of fracture. The furnace stood rebuilt and modified, its expansion joints visible as vertical lines across the brick faces. It returned to service and operated without incident for many years, but it was no longer trusted in quite the same way. The men who worked near it understood that permanence was an illusion, that even stone and iron could be made to move, and that heat, invisible and patient, could tear structures apart from the inside out.